introduction?
Yes. I leave that up to you.
This works? Yes? Okay. Okay, so welcome everyone. Thanks for coming. So this is another seminar of the series that we're building, looking, building up for the AI hackathon next year, which will probably happen around April or May. And so we welcome today Ro. Ro is a manager at Emacs Exa Science Lab. They work on scaling high performance computing issues, mainly working on life sciences problems. So life sciences, high performance computing usually work around bioinformatics, anything that goes around sequencing data, sequencing DNA data, protein folding, protein-protein interactions, and things like that. And so the idea is how to use machine learning and AI to scale these these difficult computations. And of course, how do we make sure that data governance is ensured? So, with no further ado, thank you very much. Ro.
Yes. Thank you for the introduction. Indeed, data governance, and I will focus on, because I understood AI, machine learning is important, so I will focus a lot on machine learning across data silos, and we'll see what that means. So as just explained, I'm working at IMEC in Leuven. Now IMEC in Leuven, I don't know if people know it or not, but if you know IMEC, it is very likely not necessarily for, let's say, software or AI, although we have a quite sizable number of people working on that. But AI, IMEC you might know from core semiconductor technology. So the scaling roadmap, if you buy a new cell phone or a PC and it says now it has a chip of 5 nanometers or 3 nanometers or whatever, that's what a whole bunch of colleagues are working on. So making these transistors, these chips, always smaller. So that's engineering. We're now somewhere below sub 1 nanometer in the clean room. So that becomes ever smaller. And so as a result, we hope that we can have always more powerful compute, but I will come back to that. Now, we do a lot of work there. Now, if you manage to build this type of nanotechnology, these very small structures, metal layers that you use, then you can also use it for other things. And so we have quite some people working in life sciences, for example, in using that kind of technology, but to do other things, to build sensors, for example, for DNA sequencing machines. Basically, if you look at the camera in a cell phone, that's also CMOS, a lot larger than the sub-nanometer, but it's similar processes. So we have quite a few groups that work on various sensors. That can be wireless sensors, LiDARs for in cars, imaging things, like, for example, in a sequencing machine, etc. That means that we're also we're moving up the stack. Yeah, I started at the semiconductor, then going to the technology platforms, the system and the SOC architectures. So we're moving up and we extend all the way to applications. So that means me and my team, I'm a software person. I know quite by being, I don't know, 16 years or something at IMEC. I know more and more about some of the other stacks, but I'm a software person at heart. So most of the time we focus on the software. And what is nice by the fact that we have all the rest of these things is that we can look at hardware software co-design because we want ever more compute. We also want to be sustainable. There will be another talk that focuses on that. So that means that at IMEC we can really look to bring these two worlds that are most of the time completely separate. You have companies like Microsoft that work on software, you have companies like NVIDIA that work on GPUs, and those are different worlds. They try to bring them a bit closer, but we can go a lot further. And so we're doing quite some work in bringing that work on compute hardware, processors of various sizes, to bring that closer together with sensors, and in the middle there is like this AI or this machine learning layer, because a lot of the time you use the sensors not for gathering data. Gathering data, fine, but you do that for a certain purpose. So one of the things about what we are doing a lot is looking at this, in general AI, I would say more machine learning side, and bring these two closer together so that we can have, for example, much advanced optimized systems that take advantage of your data while being in a very small form factor, or you will have a next generation supercomputer but that can do 100 to 1,000 times more work than the current generation. That's my current focus, less on the sensors. But so that's in general at IMEC what we're doing. So it's not just this hardware stack, we are extending and bringing all of these things closer together. So as mentioned, in my lab, my team, we've been doing that for quite a while, and we're doing that a lot for health-related topics, not only. And that means data in healthcare, I think we can all relate to that. And we see that data is being gathered a lot. What can we do with it in a healthcare context? And I will illustrate with healthcare examples, and then show other cases where the same type of work can be applicable. So leveraging data in healthcare, more and more we are being followed, I would say, from the cradle to the very end. And lots of data is being gathered, more and more, I would say. It's only just a start. That means that the hospital have hospital records. They keep track of what is happening, what data is being measured. If you are in an intensive care unit, then you are strapped to all kinds of machines that measure continuously blood oxygenation and various levels of toxins. That's now all being stored, and that's being kept. Before that was also gathered, but you would only get an alarm. Now more and more this data is kept around, at least for a while. And that's true to our course of life. We have these cell phone things that keep track of how many steps you walk and where you are and how many kilometers. You have smartwatches that keep track on whatever they can measure. So we have lots and lots of data related to our healthcare, related to our lifestyle. And you see that that's doctors, hospitals, insurance companies, that's your general practitioner, that can be wearable device vendors, etc. So a lot of data being gathered. And what we see then is, for example, a hospital will keep track. You have an electronic patient record, and there is a lot of information in there. That's lab results, that's whatever your doctor finds that you have at some point in time. All of that is being gathered. And as a result, hospitals are starting to use this. That it's still early because it's very complex in itself. I will, in this talk, not talk a lot about that, but it's very complex. We do a lot of work with hospitals on trying to make sense of this data, but that's not easy. But you see, they have data. They use various types of models, machine learning models, statistical models, to do something useful with that data in order to gain insights, in order to learn something. For example, to have decision support for a doctor on what chemotherapy is for that particular patient has the best chance of succeeding, right? So that's decision support. There is more and more data available, and for doctors it helps to have a machine learning context to help in taking these decisions. A hospital uses their own data. That's already practical, and we can see advantages there. But of course, there is all this other data that's also kept. But that's typically held by different parties. And your hospital simply does not have access to insurance data. And your insurance company does not have access to hospital data. And the same with pharma, the same with even your general practitioners may or may not have access to hospital data, right? Your huisdokter, I think it's a GP in English. So they may be, sometimes they have a bit of access, but certainly not everything. So even there, all this data is kept in different silos. And that's, well, more and more data is being gathered, it is available, and somehow you cannot use it, right? So you are a doctor, you cannot access what your GP is doing except for some report with 5 lines, and the inverse. That's a bit too bad, right, I would say. So the question then becomes, if we have all this data that is sitting around in all of these data silos, how can we make use of that? Because again, we'll get even more data the coming years. So we would like to see how we can take advantage of that data across these data silos. But of course, that's not easy for many, many reasons. And one of the reasons that makes it hard is that, of course, there are a whole lot of concerns to take into account, and that we also want to take into account. We do a lot of machine learning, and in the health, most of the things we do is ethical machine learning. It's not just a question of, oh, we'll do whatever we want. No, you need to take care about privacy, not only legislation, GDPR, of course, but also just from the ethical point of view. Is that a good thing to actually do or not? If you find something in the data of a patient and that patient didn't ask for this, do you tell that patient or not? Right? So there's a lot of ethical questions even regarding of the actual legislation. There is, of course, as usual, commercial interests. For example, hospitals consider whatever data they capture theirs, right? And they want to make money from this. That's already the case. If you look at trials, a pharma company goes to a hospital in order to get hospital data to set up a trial for new drugs, and they pay for that. They pay for access to this data or access to these patients. And there is a whole legislation around this. And the hospitals, of course, they have a lot of data. They would like to see, can they do more of that? So that's true for hospitals. That's, of course, also true for pharma companies, for insurance, for these smartwatches. Everybody gathers this data, and they want to monetize this. So the question is, how do you do this? Third, technical limitations. I'm not saying it's easy, but I'm actually less afraid of that. But there can be technical limitations. We do a lot with DNA sequencing. DNA sequencing is not small data. You immediately talk per patient about gigabytes of data that you want to keep for a long time. Ideally, you would like at birth, you get your DNA taken, you keep that, and 70 years later, when there is a problem and you have a tumor, we can compare both. That would be nice, except that means that you need to keep that data for 70 years. You need to pay for this, to store this, to back up this, to keep it around, to make it safe, to make it secure. So there's a lot of things you need to do. At this point, I'm the impression most hospitals actually much rather keep the biological sample because it's easier. You put that in a freezer and you keep it. And when you want the DNA in 60 years, they will re-extract it. But other data is not as easy. On that. To give an idea, when we started to work on DNA sequencing data, not the analysis, but out of the machine comes data, and before you can analyze it, that step to process from that raw data to something you can actually do something useful, processing, right, per sample, per patient. So we brought that down to, I think now we are, depending on how you do it, between 2 hours and 9 hours, but it still requires quite a lot of compute. So technical limitations, yes. And then you want to do the large analysis. What I would like to do is a population study, right? We get the genome of 100,000 Belgians, and we're going to look for patterns that we don't know yet about, yet. So that's what I would like to do. And then compute and scaling becomes an issue. So. But I'm less afraid of these technical limitations. Let's see. Good, so we want to leverage this data. Doing so is not easy. So here I simplified my silos a bit because I needed more space. So I only put 4, but there is more. For the sake of the example, I only put hospitals. That doesn't really matter. But the question is, how can we enable analytics across these data silos? And in general, I want to talk about 3 ways to do this, and I will illustrate in more detail the last, because it sounds a bit magical. So magical things, I will spend a bit of time explaining not how we do it, but at least what happens. So what could we do if we want to leverage all of this data? The first option is simple. We federate it. We put it together, right? Then we can use all data, because we tell all these hospitals or all these parties, put your data together and then we'll use it. I will briefly talk about that. A second aspect is that we do something similar, but we federate the machine learning, not the data. That's a different technique. I will also briefly touch upon that. But in the federated machine learning, we built one much better model, though that would be very similar to the one you could do when you pull all the data, but you leave the data where it is. But you built a single model. So we also looked at option 3, amalgamated machine learning, where you don't share the data, but you also don't share the models. Everybody builds their own models, they're not sharing it, but they get better by interacting with other models. So three different, I call it families of approaches. All of them in itself are technically interesting, and there's a whole lot of subparts, but these are the 3 current main themes. So the first option, what can we do? We have 4 parties. I want to have a machine learning that uses the data of these 4 parties. It's easy, I put the data together. Right? That's the first option. That happened, for example, in COVID. Right? In COVID, for a whole bunch of research projects, hospitals, pharma companies, they actually put data together so that everybody could look at it. You had all the data available in order to go faster. So in a research context, that is done quite a lot. Hospitals that collaborate, we are collaborating with a hospital, the 3 hospitals, to do very early detection of heart fibrillation. And that is something that they've already set up in a smaller way to look at this by putting some data together. Right? So that can work, but it also has a number of problems. First of all, when I say pooling data, it doesn't have to be physically in a single place. Right? That's not necessarily the case. You can do that. Everybody sends their data to a large central infrastructure and it is being stored there, and then everybody gets access to that central infrastructure. That's one possibility, but it's also possible to leave the data where it is, but to conceptually give everybody access to the full data. The key is you have access to the data, to all of the data across the parties. You can then look at governance, right? Once parts of the team. The fact that all the data is conceptually there doesn't mean that you always give access to all of the data. You can put protocols into place and tell, okay, that hospital only gets access to diabetes data of these 4 hospitals, but not lung cancer data, right? So you can put systems on top of that by nicely structuring your data, have security protocols, user rights, etc., classical IT stuff to give access to the people that you want. But typically, the key is that if you build a machine learning model there, you have access to data of more than one party because the data is somehow together. So advantage for a machine learning point of view, that's much easier to work with. You have a single data set, you can do your machine learning with that data set. The fact that it's actually belonging to 5 different people, as a machine learning person, you don't care. You can analyze all the data. So that's the simplest situation from the machine learning point of view. It is the very difficult situation for everybody else. Because you have to structure that, all your data is there. Monetization or tracking what data is being used is not always easy, let alone the impact of it in your model, not always easy. And you have then all of the GDPR legislation reasons that we're talking about. If a third party, suppose a pharma company, gets access to this pooled data in the proper way, they build a model out of this pooled data. Who does a model belong to? What happens if the data changes? Does that invalidate the current model or not? So there's still a lot of questions if you want to pool that data. But it is the easiest solution, and it is one for which you see currently at the European level, I think at the Flemish, the federal level, a number of projects ongoing to support somehow the federation of data or the pooling of data. Good. Can we do better? Right? I would say yes, we can. So the second option is federated machine learning. So when you hear federated, always check for what comes after it. Is it federated data? Is it federated machine learning? Is it federated something else? Because lately I've heard, yeah, we do federation. Of what? That's the question, right? Because this first model and this one are very different in what they can support. So federated machine learning, what is the goal there? In the previous one, we shared all the data, essentially. In this one, we're not sharing the data. The data remains where it is, but we do share the models. So that means that every party is going to learn a model on their data. The data remains where it is. We have a model learned on that data, and we all do the same. We all build our model, and then you send all of your models that you built to me, not your data, just the models. I will somehow combine them, and we will get a much better model, and then you get that model back. Right? And then we all have a better model. You can maybe train it again if you have new data. You send that again to me. I again reassemble. I send this back to you. That's how Siri works. And the Apple assistant, Siri, they train it on local data. So Apple made an initial Siri. They distributed that. That gets better by being trained on iOS machinery. And from time to time, that model is sent back to Apple. They improve and they send it back. What Google was doing was sharing the actual data in the beginning. And so they also built a better voice assistant by having access to data, so that's much more the first model. So Apple wanted to be a bit more secure, so they went to a federated approach. That actually Google invented, or at least first published about, but they were not directly using it immediately. So that's how a Siri works. So conceptually, I could do the same for my hospitals. My hospitals say we want a better heart fibrillation detector, right? We all have our patients with our own data. We all train a heart fibrillation model on our own data. We pull it together, and we will get a better heart fibrillation detection engine, right? And then we give it back to the hospitals that participate, and then we're all happy, right? So that's the reasoning for federated machine learning. And so that works well in cases where you cannot or do not want to share the data, because in this case, you're not sharing the data. It remains exactly where it is. And where you collaborate to together build a single better model. That's key. It needs to be a single better model. If one of my hospital wants a heart fibrillation detector, and the other one wants a better diabetes detector, and the third wants a better chemo decision engine, that will not work with federated learning. Because then you have 3 different models. And if you send me these 3 different models with different outputs, different kinds of data, there is no way that I can fuse them and make them into a better model to do what of these 3, right? So that doesn't work with federated learning. But if you build a single better one, nice, right? Data remains where it is, and you can do this. Second problem that you have to think about, we once tried to set up a federated machine learning model with data from pharma companies. That was valued with a lot of money. So they certainly didn't want to share the data with other pharma companies. They all wanted to have better models, right? But they also didn't want a single better model. That would be like the perfect pharma company, but they didn't care because they were all pharma companies. They didn't all together wanted to make a single new, better pharma company. No, they wanted still to have their own models better, right? So there can be business reasons for not wanting to share your models. There may be value in your model, and you say, okay, right, I don't have to share my data, great, but I also don't want to share my model, right? And if you send me a model, depending on how it is built, you can sometimes still infer some information about, not directly the data, but at least some of the directions in which that company is going in how the model is structured or built. So there may be a bit of information in that model that you may not want to share. That's why we federated machine learning, nice. But we started then working on option 3, right? Amalgamated machine learning to solve exactly that problem. So we sat together with these pharma companies, and after a while we found a way where we do not have to share the data. We keep the data where it is. We do not have to share the models because too valuable and they each still wanted their own model, but we share insights. There is something we derive from the models that we share, and as a result we don't have to share the actual models nor the data, and all of the models of the participants become a bit better, right? So I will illustrate that last one. This was the magical part, right? Seemingly you don't have to share anything and still everybody becomes better. So I will give an example of that in a healthcare context. So keep that in mind. That works well when you have these constraints I mentioned. You want multiple models, you don't have to share the data nor the models, then you can do this. So they all have, depending on your problem, various constraints, right? If you can share the data, then that's easiest, right? If that's okay and the governance is okay, legislation is okay, then you can do any type of machine learning directly on that data because it's a single data set, great. If that's not possible to share it, it's too large, it's too difficult, legislation, business, you can do federated machine learning if you want to build a single model without sharing the data. If that's also not possible because you do not want to share the models, you can go to something like this. But they all have some differences in the technicalities. Good, so 3 things, and then I put another slide that's related to security, because these two sometimes are a bit mixed. I put some terms on there that you may or may not have heard about, and that's why I wanted to drop them. They're all a lot more mathematically technical, but they come from the security angle. And the goal of security is to keep things secure. Not so much private. If it is secure, depending on who you give the key to, it can be private. But it's not the security that makes it private, that makes it secure. That means I can give you this secure thing and you can look at it and you can say, I have no idea what's in there. Right? Without the key, I cannot unlock. So, but if you have the key, then it will be very secure, but I can look into it and I can look what it is, so your privacy may not be guaranteed. So these two are related, but not exactly the same. They have slightly different goals. So in what we do, that's typically complementary. So we do some machine learning where we look at the privacy aspects, and we complement that with security, because it's not because something is private that it's secure, right? So in most of the cases, you need both. And I wanted to briefly talk about 3 things: solid, homomorphic encryption, and secure multi-party computation. Solid, I talked a bit about the hospitals and data, and that's the same with your Apple Watch. Whatever data is being gathered, Apple has it. Even though it's basically my data in a certain sense, it's about me. When I go to a hospital and I get a blood test, then the data belongs to the hospital. I don't even get it. And if I want to have an output, I can get a kind of summary. And sometimes when I ask more info, I get basically a redacted page like you see on the news where parts are crossed out in black. I once had that. So clearly it doesn't seem to be that the hospital thinks it's my data. And so there is some research, I don't know how to call it, a movement maybe. Tim Berners-Lee started this to give control of the data back to the citizens. And so that's envisioning another way of storing data, where you say, if that's citizens' data, if that's my data, then we keep that in a locker that I have access to, and from there I can give access to outside parties and I can control that. So it's a whole setup. It's a kind of a different way of thinking. The current internet works the other way around. Everybody keeps data. Your username is in, or your name and how many kids you have and what your age is probably floating around the internet in 40 and more places. But here it would be the inverse. The data is kept only once in my pod, and I give access to persons, companies, websites that need it. I give access to it. So it's a bit of the inverse round. So that's a more secure way of storing data and of deciding who gets access to what data. In how far this will work, still under full construction. As IMEC, we do quite some work in there, in a lab in Ghent. And that's, we'll see how it pans out. Part of it is a technical issue on how to do that properly. Part is then a different mindset. Will that work? I don't know. Will we in the end be able to convince Apple that all this data that is on my smartwatch comes in my data pod and not on an Apple server? That might take a while, right? So, but there is other cases where we already have collaborations with companies that start to do that and that keep indeed the data in a pod and ask access to it. So it's we'll see how far we get, but that's a way to store data and give access in a secure manner. Then two techniques. Looking at the time, let's see. Oh yes, good. Two techniques I want to briefly mention. I will not go into detail. I think each of them is about an hour explanation if you really want to have a better understanding of what's going on. One is homomorphic encryption, and I already talked. I explained, okay, I can give you data and it is encrypted. Now suppose I want to do something with that data, because again, data by itself, we don't care. Right? I want to calculate something with this. I want to do something useful. So what normally happens, if I send you some encrypted data and you have the key, you decrypt that, you look at the content, you, I don't know, you increment it with the number of patients that have diabetes. If you need to do that, you encrypt that again and you send it back to me. Right? And that means the data at some point is unencrypted. I can look at it, I can add whatever I want, I encrypt it again and I send it back. The idea of homomorphic encryption is to send this encrypted data around, right, and do operations on it. For example, I can add my number of diabetes patients to that encrypted number, but I do not, that number is not unencrypted, and I cannot see what's inside, but I can still add to it. Right? So I sent you something, I have 5 diabetes patients, I say +5, that it remains encrypted, it gets internally added to whatever the value is, it gets incremented by 5, and you pass that to the next one. And so, for example, you can do a calculation across many places, like an average age of patients or whatever, and you will get the average age, and nobody will have seen until at the very end, whoever has the actual key to encrypt it will be able to encrypt it and see that value. But that person will then not know what the ages were of all the places that were visited. So that's the idea of homomorphic encryption. You keep your data encrypted and you can still calculate with it without seeing what's inside. Right? That's a fun technique. Calculating the encrypted domain. Very interesting, very useful. The only problem is that at this point it's between 1,000 and 10,000 times slower to do calculations, because it remains encrypted and it becomes very complex to do these operations. So it's fun we typically combine it with parts of what we do, where we do some parts with homomorphic encryption, but if you want to do, let's say, a somewhat bigger machine learning exercise, you can, at this point, you cannot afford the time. Right? Technically, it will work, you cannot afford the time. We're also working on trying to see if you cannot speed that up in hardware, this hardware software co-design, but that will still take a while. So very interesting if you have calculations like averaging and logistic regression, not too complex things that you can do with homomorphic encryption. More complex, it's still too slow, but we may get there. Right? But again, it is a security technique. It's probably the one that is closest to privacy, because the fact that you cannot look inside because of security reasons is also interesting from a privacy standpoint. But the goal still is about security. And secure multi-party computation is another security technique where the goal is to have the results and the computation being done at multiple places without seeing what is happening, and again using encryption to keep all of that secure. So that computationally is much better than this homomorphic encryption, but you require a lot of communication because there is a lot of messages being sent around. So if your data becomes a bit bigger, then purely network-wise, it becomes, in that sense, very costly. Not the computation, but the sending around. So typically we combine them. We use homomorphic encryption, secure multi-party computation with this federated or amalgamated machine learning for parts of it. And then you can get to interesting combinations. Good. I promised a bit of magic. So amalgamated machine learning in action, since I didn't know the level, I didn't go into a lot of, not even a lot of, I don't go in technical detail, but I want to see what you can accomplish with that, because that's probably more interesting. So what's the goal of our amalgamated machine learning? To preserve privacy and to preserve IP. And like I mentioned, there is we have several examples where there are multiple data silos, typically under control by different entities, that want to do something with that data, which is not the same as the other entities, and they still want to collaborate without pooling the data. And yeah, pooling the models here, they don't even want to pool the models, but it wouldn't be possible because they want different things. So even if they could, federated machine learning will not help. And I will illustrate this with an example from healthcare, because we can more easily relate to it. It's a slightly artificial example, and I will explain why in a second. But we're going to do machine learning across 4 parties: a doctor, a blood labo, a hospital, and a hospital labo. So 4 parties that have some data. They will each have their own model that they want to build, and they want to leverage the other party's data. What did we do? The key are these amalgamated features. How to calculate them depends a bit on our machine learning technique, and so I will not explain, not here. But that's actually not just a technicality. So we did some work on ICUs, emergency rooms in a hospital. And there is a data set, a publicly available data set, the MIMIC data set. You don't need to, I will explain a bit what's in there, not that important. But that's a data set that's been gathered by MIT in the US with around 60 to 70,000 patients in an ICU. Right? And they measured from these patients 82 things. And it's a bit small, I just want to give an impression, but that's like temperatures and various levels of oxygenation, measurements of urine, measurements of blood, a whole bunch of measurements that you do at an ICU. And they made that data set available. There is four things in there that relate to something called acute kidney injury, which is something that happens quite a lot on an intensive care unit. Where patients develop after a while problems with their kidneys, acute kidney injury. I'm not a doctor, so we sat together with doctors. We found in this publicly available data set 4 measures. One that predicts the AKI in 7 days' time. So it will just say in 7 days' time, patient has AKI, yes or no, right? Other measurements do the AKI, but you can have AKI kidney injury in different stages, different gradations, from really bad to not so bad. I think that there is 4 stages. You can predict it. You can measure this AKI stage in the creatinine, and you can measure it, so basically 1 in blood and 1 in urine. And the 4th one is the AKI stage in 7 days. So they're all related to AKI, but different, right? And that's why we went with 4 parties. And in this data set, that's all from a hospital. So there, that's like pooled data. All the data is there because that's from that hospital. So we decided to cut this up in 4, just for our experiment to be able to compare to a full data set that is realistic because it's actual data for which we can talk. The reason we took AKI because it's a very well-known model. If you look for AKI models on the internet, you will find various AKI models. So if we built a model, we could compare. Because I'm not a doctor, if that model tells me your accuracy is 74%, I don't know if that's a good model or a bad model. I cannot tell. But for these models, we could compare. Now, the first test, that's like the pooling data, right? In this case, it's easy. The data was already pooled because it's from a single place. But so in our little game, we imagine that the data would be in 4 places and that we pool it. We make it available together. And then I can do machine learning on that data. That's the first case, right? Now, in our setting, we have 4 parties, and you see the top 2 lines, there is prediction, target, and the machine learning technique. So they each predict something else. It's all related to Aki, so that I can compare, but it's a different target. It's the 7-day, and the 7-day stage, and the one with blood, and the one with urine. So they each have their own target. And they use different machine learning techniques or different settings for their technique. For the hospital, we used neural networks, a deep neural network that we built. For the other 3, we use decision trees. That's another machine learning technique. I'm not going into detail, but you build a tree of options that in the end, in the leaf tells you, oh, I think it's this, right? And you build this tree, you learn this tree. That's a decision tree. For our health cases, we use a lot of decision trees because you can actually show them to a doctor in the end. And a machine learning technique, it does something and it typically works well if you build it right, but you cannot explain what is going on. A decision tree, I can actually have a look and I can say, okay, these are the decisions that are being taken. So we use a lot for our health cases decision trees. So we use 3 times decision trees, but like with deep neural networks, you still have a lot of choices. You can go for wide decision trees, deep decision trees, combine multiple decision trees, use different values. So they all use decision trees, but a bit differently. And what you see then, I have then all of this data available, and my doctor trains a 7-day Aki decision tree and gets to an accuracy of 90%. Right? Not too bad. The creatinine one, 79%. The neural net hospital for the urine Aki stage, which also in literature performs the best. It's what most hospitals use, 95%. And the labo, also with decision trees, the 7-day Aki stage, 87%. So if I pull all the data, I can build models for these targets that make sense. And we checked in literature that's actually comparable to what you get with actual models that hospitals really train, spend a lot of time to optimize. We worked with UZ Leuven doctor on this for Aki prediction. So then the second experiment, we create our data silos. And we went over the data. First we did it, and then we let some doctors look at it. It's a bit artificial, right? Because the data was meant to be a global one, so we put some artificial lines, but we took care that, for example, the doctor, there is an entry there about alcohol abuse. That's typically something that your general practitioner may know, but not your blood labo, right? They typically don't care, they don't have this information. So like that, we tried to group it to somewhat make sense between these 4 parties. So now we have 4 data silos. We can do the following. What if I do not want to pull my data and I cannot use this amalgamated machine learning? What can I do? Then I have these 4 parties, and now they're using only their own data, which is very realistic. That's currently what happens most of the time. They use their own data, and then of course you see that the results are not as good, right? Which you can imagine because every party now has a subset of the data. And we know, for example, that I think in blood or urine, one of the 2, there is some features in there that are quite important. So 3 of the parties will not have access to that feature, right? So they will perform less by definition. But that's in reality the same. If Apple wants to predict me something, but they would need to have some medical information, they don't have that information. Try what they want, they cannot use it because they don't have it. So what you see is there that you see, they perform worse. For example, the hospital and the hospital labo, 47%, that's a coin flip. 50%, I have 1 chance in 2, so I might as well not do it. So they clearly don't have the right data. So what we can then do is apply our amalgamated machine learning. And that means that we have these 4 data silos, still the same. But at the very bottom, you can see that you have a bit more information. You have your own local data, but you also get amalgamated features from the other parties. Information that we derive from that party, not a model, not the data, something we derive. And that's a more technical thing. People that are interested, I can tell something more later. But we derive this extra information, and that means you have more data to use, and it is relevant data for your target. And that makes it fun. What we see if we do that, that we then get to numbers, accuracies that are actually close to the pooling of the data. So there is a bit, decision trees have a bit of randomization. So in the bottom right, we even do a bit better, right? Of course, if you would do 30 runs, it would probably average out to be the same. I think here we did 5 runs. So what we can see is that by doing this trick with these amalgamated features, we get back to very similar results, I would say, than pooling the data. We've seen that on a lot of examples. This is one that I can easily show because it's a public data set, so you can check it. Good, so everybody can build their own model, can use their own data. Data remains in the silos, and we still get good results. But it's a relatively complex technique. Since if I have just my data pooled, I can use whatever technique I want. I have my data set, so to work with, that's easier. Here it's a bit more setup. In practice, that means that still data needs to go, derive data from one hospital to the other. It's not a lot, but that means practically we need to talk to hospitals. We need to make sure that there is an infrastructure there that they trust. There is something running in their hospital that does something, that sends data, that gets data back. So it works, but it took some time. We have a number of hospitals that are now participating in such schemes, but that takes time because that's much more difficult than for me to say, okay, here is your data set, work on it. That I can just do, provided I can get all the ethical things right. Good. And multiple techniques. Okay, let's see. Oh, good. I'm more or less in time. So I wanted to talk about not so much data. I wanted to talk about what you do with the data, which is why I want to keep data. I'm not interested in data, actually. I'm interested in what can I learn from the data. So the question is how to do this across data silos. And so we looked at 3 different ways, 2 of which that are relatively common. Federated data, basically putting your data together somehow. Federating the machine learning, so building your models on this data, keeping it where it is, but exchanging the models to make a better model, or this amalgamated machine learning where you go even one step further for cases where it works. And so we illustrated this with this Aki case because it's more or less understandable, or at least I can show some of the benefits easily. We have also done that outside of health. You have exactly the same type of problem when you look at complex production pipelines, where you have multiple machines in a row that together in the end make an end product. They could each optimize their working if they would know more about the total chain, but they also typically don't want to share data. That's very, very similar. So again, there we can apply the same amalgamated ML or federated ML, or you can pool your data, and you typically find combinations. I know the clean room, I talked about it earlier. That's one of these complex production processes, and there, for example, these machine vendors already share subsets of data, right? But not actual data because they're very paranoid. All these machines are very expensive, and each company makes one type of machine. So if somebody cracks the code to building a competitor, then suddenly your market is gone. So they're very, the data that they gather and what their machine does, they keep that very secret. So they share a bit of data, but the least possible. So there again, we can do something more. Same for autonomous guided vehicles or automotive. You have cameras all around that are taking pictures. You will have cars. How do you exchange this data, right? So again, we can do various techniques to make that possible, where you also get fun things that you need to think about, like how many data am I sending around, right? For example, sending raw data from a 4K camera that is sitting in a room there and sending that to another place, that consumes quite a lot of network bandwidth. So if you want latency, network bandwidth, and you have multiple of these cameras, just from the purely technical point of view, that's already difficult. So not just privacy, also technically, there is things we can do there. And then for pharma companies, you can also do this. I will stop here.
did you compare or compare the performance of the three of them?
So in for the Aki, we compared the first one, so pooling the data with the last one, the amalgamated. We didn't do federated there because they each had different models. So we could do an experiment, which we didn't do, to train a model, 4 models then, because we have 4 different outputs. So to train 4 different models across these 4 different parties and then compare, but that we haven't done. The reason is that federated machine learning, I made it sound very easy, right? You have a trained model and another trained model, and you put these together, and then we have a magically better model, right? But that's very hard. So there's a lot of research going on there, especially on doing that with deep neural networks for images. And there they start to learn a bit, okay, so if you have these weights in this model and these weights in that model, if we cannot just take the average, that will not work. So can we then take a maximum or a minimum, or how do we do this? And for images, there start to be techniques that work, but these are not images here. Here we have different types of models, and that there is still a lot of work going on in how can I combine this? If I get 2 trained networks and I put them together, when do I have a better one? So that's why we didn't do an experiment where we trained 4 networks for this type of data. That would in itself still be quite a lot of work. But if it's for images, there you start to have, I think NVIDIA even has a publicly available tool to help with that, but for images, deep neural networks and images. Doing that with something like decision trees, not images, much harder. So that we didn't do. So typically for us, when we need to choose between these techniques and subsets, it's about what are the constraints, right? Can we share data or not? Can we give access or not? Is it okay to share the model or not? And that will largely define what we can do. So in that sense, we compare against the pooled case to see does it make sense, but in the end, the actual comparison is with using only your own data or the other version. Do you improve there or not? Because that's the actual benefit as a party that is investing in this scheme. That's what you will gain. And the fact that you might gain even more if you would be able to pool the data, yes. Right? If my car would fly, then I could go much faster to Ghent. But if it doesn't, then yeah.
Coming from an online user, visitor. So applying federated data approach requires to have a federated process for data collection. For example, number of COVID-related deaths versus admissions. Is this currently checked before using data silos?
It's another layer. So regardless of which of the techniques that I presented here you use, there is still that question. How do you get to data in the first place? So if I understand the question, it's like, can we put multiple ways to look at it? Can we know something about the quality of the data? Can we know something about, can I compare data? If one hospital inputs data, another hospital inputs data, is it actually the same? If it comes from a different device, and one device measures from 1 to 10 and the other measures from 1 to 7, and I need to compare these, what do I do? So that's really about the semantics of the data that is being kept there. Yes, is it standard or not? Can we standardize this? Can we standardize this? What are we doing? So in the pooling of data and in the federated machine learning, there you expect the data to be the same. So there this standardization has to be done. And we see that's still very complex. And again, I talked here about a lot of medical data. That's a lot of the time that's very complex because you need to sit with doctors to understand what is the meaning of that parameter in that hospital that is being put there, and in the other hospital they put something related but not quite the same. When can we compare it? And so you need to make these data sets homogeneous and semantically the same so that you can reason about this. When you pool the data, you need to do that because it's one data set in the end, so it needs to be the same. When you do federated machine learning, you need to train the model on that data, and still it assumes that it's the same model on the same data with the same semantics. With the amalgamated machine learning, we haven't done the exact experiments, but there it is not necessarily the case because you train a model on data in one place and you only get derived information. That means that if this is different values and a different model, that's still okay. I don't even need to know how it is calculated. That's why we keep the privacy. And that means that this very strict homogenization is not needed as much. But we're now looking into more concrete experiments to get there. But that could be another difference. And that's, we didn't set out for this. It's a kind of side effect from the fact that we wanted to keep the privacy, that we don't want to look at the data and we don't want to look at the model. But as a result, we don't have to look at it. So if it's slightly different there, that's actually okay. So there is ongoing work, but you're right, at this point that is complex. And in the collaborations we have with hospitals, when we look at the federation and when we look at the pooling of data, that is still a very large and difficult step. And it's one that's very hard to automate because it's about the semantics of the data that's in there. If I could automate it, that's fine, but that's typically not the case.
Any more questions? So maybe I have one touching on the security. You mentioned solid. So you said today we have our data spread across different 40 places somewhere in the internet. Now we could come with a solution where we have one place where we are responsible for holding our own data, and we give access to vendors to access that data. What are the mechanisms that ensure that the vendors are not copying the data again, and then that the model of 40 or 60 or whatever happens again?
The copying of data, I'm not a solid expert, but I asked them the same question, right? And it's the same question you have with pooling data, because essentially with solid, it's in essence, it's a kind of different way of pooling data, right? And as soon as you pool data and you give access, that's also true for this first technique. So we have data pooled, and I have access to access all diabetes data. At that point, when I have access, question is, can I copy it out or not? Right? With solid, that's the same. So I say, yes, this company has access to my age, right? And maybe they copy it again, and they will never come back to me to ask my age, because they also know you just increment it by 1, and then it's okay. You only need to ask that once. So in solid itself, solid is just, between brackets, it's not easy, but it's just a data storage. And so we're looking with them on doing the compute directly close to that, so you don't have to give out the data, and so you cannot copy it, right? So that would be a way to go around that problem, because any type of setup where you give access to something, right? At this point, it's digital. In many cases, you can just take a copy, always. So when pooling data or with solid, if I get access to the data, instead of doing +1, I can just take it out, right? And if that's data that over time changes, that may be okay, then there is a kind of life expectancy on when it will be valid, but that's not always the case. So that's also one reason why for the giving access to data, I would much rather always bring the compute to the data and get the result back than giving out access to the data, because it's very hard to get right in general.
Thank you.
Good. I can just